Welcome back. In this video, we're talking about an example using the Wronskian for proving that solutions to a constant coefficient second order linear homogeneous ODE are linearly independent. Okay, well, it doesn't make any sense to take the Wronskian of something where I don't actually know what the functions are. So let's use the characteristic equation to actually find the solutions, and then we will verify with the Wronskian that those are actually linearly independent. Okay, so here we go. So remember the characteristic equation for constant coefficient homogeneous ODEs. How do we do that? Well, the characteristic equation, okay, and I got multiple videos on characteristic equations, so go and find those. You'll see various examples worked out. Characteristic equation is r squared plus 3r plus 2. That's equal to 0. Now you hope that that factors. Okay, well that factors as what? R plus 2 times r plus 1. That's equal to 0. So that means that my roots are r equals minus 2 and minus 1. All right, so that means that my solutions are given by y1 equals e to the minus 2t and y2 equals e to the minus t. All right, so those are my two solutions. Now, if these two solutions are linearly independent, they are. We're going to verify that in a second. But if, when we show that they are, then I know what the general solution is going to be, okay? And we'll write that down. But let's write out the Wronskian. So I have the Wronskian of y1 and y2 as a function of t, okay? So this is the determinant of, okay, y1 goes in first, so e to the minus 2t. The derivative of that goes below it, so minus 2 e to the minus 2t. And then y2 goes in the next slot, e to the minus t, and its derivative right below, minus e to the minus t. And I take the corresponding derivative. So remember, that's going to be this term times this term. So what will that be? Negative e to the negative 3t. So minus e to the minus 3t. And then I have to subtract the product of these two. Okay, so that'll be a negative 2. So I'll put a parenthesis, minus 2 e to the minus 3t. Right? So just double check. Okay. And what do I end up getting? Minus and then plus 2. So I get a plus 1 overall. So that's e to the minus 3t. And that is never, not only is it never equal to 0, it's definitely not the 0 function. So what does that mean? That means that y1 and y2 are linearly independent, and therefore, okay, so these little three dots, therefore, the general solution to this ODE is given by y of t equals c1 y1. Y1 was this guy, so e to the minus 2t plus c2 e to the minus t. That was y2. And there is my general solution, which is given as a linear combination of the linearly independent functions e to the negative 2t and e to the minus t, both of which are solutions to my ODE. And therefore, if I think of these as basis vectors for my solution space, and they're independent, I've got two vectors that are independent, then their span is a two-dimensional space. The dimension of that space is the order of my ODE. That's not an accident. Okay, so there you have it. That's how you use the Wronskian to verify that solutions to an ODE are linearly independent. Again, I'll always ask to like, subscribe, share with your friends, comment down below, give me questions to work out. These are, after all, my office hours.